Okay, today we're going to talk about related rates. What's the motivation behind this? Well, common problem. Let's say I have a ladder. I know my green ladder is beautiful there, leaning against the wall, and it starts to fall down. So the rate at which it's falling down might relate in some way to the rate at which it's falling or being pushed away from the wall. So downward rate, outward rate. And related rates problems, we're going to be able to figure out one of those rates if we know the other one. So this is really actually kind of super beneficial. We can find the rate at which a tank is leaking if we know maybe something about the change in the volume. What I'm getting at is these are really, really good application type of problems. Having said that, I like to think of these as basically implicit derivative word problems. So we're just going to be doing a lot of implicit derivatives for a bunch of different equations and solving for one of those rates, much like how we were solving for dy dx in the last section of Unit 2. Same idea. The difference is the word problem part tends to throw people off because you got to come up with your own equations. If you follow this process, though, or hold on, I guess I'm getting ahead of myself. Just as a quick refresher on doing different implicit derivatives, I did want to mention we are typically going to be differentiating with respect to t because a lot of our problems are going to be dealing with time. So just as a refresher, let's say I had this equation with a bunch of different variables and I differentiated with respect to t. I just apply d dt to both sides, use all of my correct derivative rules. Any variable that is not a t, I need to have d, that variable, over dt. So it would look something like 2x dx dt minus 1 dy dt equal to 1 dz dt. Typically, we will have an x value that we can plug in, and we will have a value for either dx dt and dy dt or dz dt and dx dt. Typically, we're just going to have one of those rates that we don't know, and that's the one that we're going to solve for. But I wanted to run through that quick refresher of doing implicit derivatives. Anyways, the process I was alluding to a second ago and kind of stumbled. If you follow this process for all of your related rates problems, this will really, really help you organize your thoughts. If you don't, it doesn't mean you won't be able to solve a related rates problem. It just makes it really difficult because you're going to get lost in your own work. What is this process? Well, I call it given, find, when. This is really common among calculus teachers, and it's really just a tried and true method. What does that mean? Well, typically you'll be given some information. Usually this will involve some kind of rate of change. Maybe it's how fast a kite is being flown above you. Maybe it's how fast an angle that a fishing line is making with the water. All kinds of different rates are going to come up in the given. Also, things like maybe it has to do with an area of a circle or perimeter of a rectangle. You will be given information, usually will have some kind of rate in it, and maybe some additional information. Also, the find, that's usually the rate that they want you to find. Given how fast the ladder is moving down, figure out the rate at which it's moving away from the wall. Or conversely, that ladder, if you know how fast it's moving away from the wall, find how fast it's moving down the wall. And then you will typically be given a point in time or a value to plug in. So you want to be able to break down all of these related rates questions in given, find, when, and then you do the work. So this is the setup, but if you do this setup, I guarantee it will make your life a lot easier. So just as a quick example, let's say we have an area of a circle that we know is increasing at a rate of 45 centimeters squared per minute, and they ask us to find how fast the radius is changing when we know the radius is 12. Okay, so you need an equation to tie all of these problems together. Obviously, in this one, we would probably use the area formula for a circle, pi r squared, but I'm not going to get that far. I really just want to focus on the given, find, when. We're given the rate of change of the area. So the given is actually a rate. It's how fast the area is changing over time. So that would be dA dt. So given dA dt equals this, and we know that it's increasing because they said so, it could be decreasing. In that case, we would have minus 45 centimeters squared per minute because the rate can be negative. The thing they want us to find. Okay, so they're asking find how fast. So the find is going to be dr dt. how fast r is changing with respect to time. That's the rate of change of my radius. And when, so that's when r equals 12. If r equals 12, typically when we set up this problem, we'd have that area formula for a circle. We would plug that 12 in and be able to find an area and go from there. Now, I'm not going to follow through on an entire example, but I really want you all to focus on the given, find, when. They're going to be different in every scenario, but if you break them down into these three parts, it will really, really help you out in the long run. That's it for this video, and you should have plenty of info for those questions on Schoology.